high school science, you've heard of the 3 laws of thermodynamics. The first one is most popular. Energy can be neither created nor destroyed. So law of conservation of mass and energy. We're going to talk about that one a little bit, but what we're going to focus on is number 2. Number 2 says for a spontaneous process, the entropy of the universe will increase. So we're going to talk about what it means for a process to be spontaneous, and then we're going to talk about what entropy is. The third law also pertains to entropy, and we'll talk about that one a little. The entropy of any pure crystalline substance at a temperature of 0 Kelvin is 0. And what this does is provide a reference point for entropy. So let's look at what thermodynamics is first, and we'll talk about the first law. So thermodynamics really just means the transfer of heat. We're just following the heat to determine what the reaction is going to do. In a closed system, meaning a system where you can't transfer a material or matter, energy can be transferred. And energy is transferred in the form of heat and work. So in order to look at heat and work transfer, we're going to define our system and our surroundings. So a system is whatever we're interested in. That could be a reaction, it could be a balloon, it could be a piston. So whatever process or system we're interested in, we label as the system. The surroundings then is going to be everything else. The air around our reaction, the table our beaker is sitting on, the external air outside of the balloon, all of that would be considered the surroundings. So our first law says that we can transfer energy, we just can't create it or destroy it. So when we transfer energy then, we can define a change in energy for a system or a process. So delta E represents that change. Do we have an increase in energy or a decrease? We can measure this energy change based on Q, which is our heat, and W, which is our work. Alright, does heat go into a system or leave a system? Is work done by the system or is work done on the system? We can also calculate change in energy by taking energy of the final state minus energy of the initial state, because energy is a state function. So it doesn't matter how you get there, it only matters where you start and where you end. So by taking the difference of the final minus initial, we can get the change. Now when we do this, we can get a positive or a negative value for delta E. Negative means energy is lost from the system to the surroundings, and positive delta E means energy is gained by the system from the surroundings. Alright, so if our first law of thermodynamics describes heat transfer and work transfer and energy change, why do we need any other laws? What else could be happening? And if we think about a system where heat or work is being transferred, we can immediately start to see the problem. So if we imagine our hot cup of coffee sitting on the table, we know that if we leave it sitting there, the hot cup of coffee will get cooler. Heat is going to be transferred from the hot cup of coffee to the air and the surroundings. But we also know eventually it will stop getting cooler. So 2 things there. Number 1, why does heat transfer from the hot coffee to the room instead of the other way around? Why can't my coffee get hotter? And number 2, since it does cool off, why does it stop? Okay, why would it stop getting cooler? So obviously we know that heat transfers from the hotter object to the colder one, but the first law of thermodynamics doesn't explain why. It doesn't talk about direction of heat transfer. Secondly, We also know the hot cup of coffee is going to stop cooling off when it reaches the external temperature. But again, the first law doesn't explain why that is. So we're going to look at the second law to figure that out. The second law says that for a spontaneous process, the entropy of the universe is increased. So we're going to talk about what spontaneous means. A reaction or a process is either spontaneous or not non-spontaneous. Spontaneous means it can occur without any outside influence or help. We don't have to do anything to make it happen. If we take a glass of water outside on a day where it is below freezing, the water will freeze into ice spontaneously. We don't have to do anything to make that happen. Non-spontaneous means that it will not occur unless there's some outside influence that causes it to happen. So if I take an ice cube outside on a really cold day where it's below freezing, it will not melt unless I do something to make it melt. So I'd have to apply my own heat. So that would be non-spontaneous. If a reaction is spontaneous in one direction, it is non-spontaneous in the reverse direction. So my water freezing outside when it's very cold is spontaneous. Trying to melt it while it's still very cold would be non-spontaneous. I would have to provide a heat source. Alright? Now, the energy required for non-spontaneous reactions is sometimes so great that it's not possible. So imagine an egg falling off a counter and hitting the floor and smashing into several pieces. The smashing of the egg would be spontaneous. We didn't have to do anything to make that happen. That's just going to happen every time. But we never see the egg put itself back together and jump back on the table because the reverse reaction is so non-spontaneous that it never occurs. Now, some reactions are not that unlikely, but we can get the idea. Now, one warning, spontaneous has nothing to do with time. So, a reaction that is spontaneous can be very slow. It doesn't have to happen quickly. So how do we know if a process is spontaneous? There are some things that we can look for. Spontaneous reactions normally have increased movement of particles. So this could be speeding up the particles, it could be giving them more space. Increased freedom of movement can involve breaking them apart into smaller pieces so that they can now move more. Or even phase change, so vaporization of a liquid to a gas, so increasing the temperature, allows the separation of the molecules, so now they have more freedom, they have higher kinetic energy, and they're farther away from one another. That's going to increase the movement of the particles. Other possibility is increasing the number of particles, so a large complex breaking into smaller pieces. The smaller compounds can move more, and energy is dispersed over more of these particles. Dissolving is an example of this, along with breaking down a complex compound. So dissolving a salt, we're breaking an ionic compound into its ions, so that would be increasing the number of particles. And the last characteristics of a spontaneous process is dispersion of energy over more levels. This can be an increase in size, increase in molecule size, as well as atom size. Alright, so how do we know if we're getting more particle movement, more freedom of movement, more numbers of particles? And the answer is we measure this in terms of microstates. Microstates is a position and an energy dispersal for a molecule or atom or process. at a particular point in time. Every time our position moves or our energy dispersal changes, we can take a different microstate. So we can think of this in terms of taking a picture of something. If we take a picture of something that is moving, an animal or a person running, we would take a picture every time their position changed or their energy level changed. We could take millions of pictures as long as something is moving. Every single one of those pictures would be a microstate. But if we take a picture of something that is still, like a statue or a building, we really only need one picture because it's not going to change. It doesn't change position, it just doesn't change energy, because it doesn't move at all. So we would only have one microstate for that statue or building. So the larger the number of microstates we have, the more spontaneous that it is. Alright, let's look at how a process would work with this idea of spontaneity. Alright, I have two sides of a connected container separated by a cock stop. If I have it closed and I only have gas in one side, but the other side is empty and evacuated, means we've removed all of the gas and air and everything, nothing will happen in this container until I open the valve. But as soon as I open it, I know that the gas from side B is going to rush over to side A. But the question is, why does that happen? That is a spontaneous process, opening the valve and the gas moving across, because I don't have to do anything to make it happen. As soon as the valve is open, the gas is going to move. I don't have to force it to move. I don't have to apply any pressure. That is a spontaneous process. But why is that spontaneous? Why does the gas move? If we think about gas on side B being 1 atmosphere, when we open the valve, we notice that once it reaches equilibrium, we have 0.5 atmospheres on both sides. So approximately half of the gas from side B moved over to side A. Why only half? Why didn't all of it move? And the answer to that is the same answer of why it moved at all. The gas molecules are trying to gain as much freedom of movement as possible. If we imagine that they're crowded inside B, having more space allows an individual gas molecule to get further away from its neighbors, which allows it more movement. It eventually settles on an even distribution between side A and side B because this configuration gives the maximum amount of room to all gas molecules. This is as far away as every gas molecule can possibly be in this final equilibrium setup. So it's the most spontaneous, and this is where it stops. But now if I wanted to push the gas over to one side and go back to side B, that's not going to happen spontaneously. It doesn't matter how long I leave the valve open, the gas is not going to move back over to side B because there's no incentive. Crowding all the gas molecules back together would decrease the freedom of movement. So that would be a non-spontaneous direction. Now I could force it to happen by applying a pressure, but that's part of why it'd be non-spontaneous. So if we look at all these microstates, and we look at increasing the freedom of movement, increasing the number of particles, increasing the dispersal of energy, it all leads to this idea of entropy. So entropy is proportional to the natural log of the number of microstates. The more microstates we have, the more entropy we have. So entropy is a measure of disorder. It's a measure of how many different combinations or ways we can arrange our molecules and our energy to represent the same value. So if we imagine this like a deck of cards, how many different ways can we arrange our 52 cards in a deck? No matter which order we put the cards in, it's the same cards, it's the same deck, it's the same size, but we have several different ways we can arrange that deck. So there's a lot of entropy, there's a lot of disorder. So we're applying this idea to processes and reactions. So the more microstates we have, the more ways we can order something, the greater the entropy. So our second law says that for a spontaneous process, the entropy of the universe increases. Alright, so if we have a process or reaction that is spontaneous, it implies that the entropy of the universe must get larger. And we know this is true. Our world tends toward disorder. It's easier for things to fall apart than it is to be put back together and properly arranged. And properly arranging things in our world requires effort and energy. Now, let's look at entropy in terms of an isolated and then non-isolated system. In an isolated system, we have to have an increase in entropy. Natural processes that are spontaneous have an increase in the entropy within the system. There is no influence from the outside. But in a non-isolated system, like most of the reactions and everything we come across in our daily lives, the entropy of the system is also affected by the entropy of the surroundings. And we have to consider both the entropy of the system and the entropy of the surroundings to determine the entropy of the universe. And the entropy of the universe is what needs to increase for a reaction to occur spontaneously. Alright, so let's look at our two values. Entropy of the system describes how our particular system can be arranged in a certain manner. So think about our deck of cards. How many positional disorder arrangements can we make? How many different ways can we have shuffle our deck of cards? Alright, and then entropy of surroundings is really the energetic disorder. And for processes and reactions, this applies to the heat transfer. We need delta S of the universe to be positive for a spontaneous reaction. Therefore, delta S of the system plus delta S of the surroundings needs to be a positive number for a spontaneous process. So we have four different ways this can happen. If both values are positive, then of course it's delta S of the universe is positive, and it'd be spontaneous. If both are negative, we have to get a negative value, then delta S of the universe would be non-spontaneous. If one's negative and the other's positive, we then have to look at the larger value. Alright, in the next video we'll look at doing some calculations with entropy and also looking at entropy within an atom or a molecule